Hello, my name is Vishal Sharma and this is my demonstration video for the task Above and Beyond. The requirement of this task was to go beyond the course material that was taught in the duration of the semester, and in this video I will be sharing the evidence as to how I have achieved all this. Now the first thing that we were supposed to do was to research on SMTP, which is used to transmit email messages from the sender's email client to the recipient's email server and is responsible for sending and receiving emails between servers. The foundational structure or architecture used in application layer protocol is client-server architecture. A mail server responsible for communication between the clients. Each client receives and sends messages through that email server. SMTP, the transport layer protocol used for email communication, uses TCP/IP at port 25. When an email is sent, the SMTP client on the sending computer connects to the receiving computer's SMTP server and issues a sequence of SMTP commands to deliver the message. This is the simple email communication process. A writes and sends an email to B. Mail user agent creates email messages for transfer to the mail transfer agent. MTA receives the message and transfers the message from user A's client software to user B's email server, and this communication happens through TCP at port 25. User B's email server receives the message and lands in the user's mailbox via the MUA at B's end. This is the overview of SMTP. Now, coming up next is TLS. So this was the steps I took to analyze TLS handshake in Wireshark. First of all, cleared my browser data and closed all the other applications accessing a network, starting Wireshark packet capture, going to any website using HTTPS, pause the packet capture and analyze the handshake. Now, what I've observed: client sends a message to server to set up an encrypted communication. The packets include cipher suites, SSL, TLS versions, and the client's public key. Now, from the server side, it responds with the selected cipher suite. It ensures that the TLS version used by the client are supported. Along with this, the server shares its certificate and public key. Coming up next, we have the need for congestion control in TCP. So my research suggested that TCP is primarily used for reliable data transmission. It ensures that all packets sent are successfully transmitted and received in order, that is, no packet loss occurs. However, there are some limitations to network resources, such as buffer space, bandwidth, which are limited. When a lot of data packets are transmitted simultaneously, it can lead to network congestion. Network congestion can lead to increased delay, reduced throughput, packet loss. This reduces the network's overall performance and reliability. Now, congestion control helps in this. It regulates the rate of packets being sent, number of packets in transit at a time. Congestion control employs dynamic transmission rate based on network's packet loss and delay to avoid overloading the network and ensure fair sharing of the available resources. It helps in maintaining the network's overall scalability and performance. Coming up next, we have flow control. In order to guarantee dependable data transmission over a communication connection, sliding window algorithms are used to ensure flow control. Let's look at them one by one. First, we have stop and wait protocol. A single packet is sent to the recipient using this 1-bit sliding window protocol, and the sender then waits for an acknowledgement before transmitting another packet. The stop and wait protocol sends only one packet at a time. It results in low network utilization. Due to timeout period for each retransmission in case of packet loss, a sizable delay is associated with this protocol. Coming up next, we have go back n. The sender in the GBN protocol keeps a window of size n packets, which is the highest number of packets that can be sent before waiting for an acknowledgement. For each of the first n packets it receives, the receiver transmits an acknowledgement message. Quick and effective, but can cause inefficiency when there are a lot of errors or delays in the network. Selective repeat. It is comparable to go back n protocol, but instead of retransmitting the full window, it can only send the lost or corrupted packets. The sender sends n packets and then listens for individual acknowledgements for each of the packets sent. The sender retransmits only that specific packet rather than the complete window if an acknowledgement for a specific packet is not received within a given timeout period. Now let's look at the differences between all these protocols. Window size and retransmission. Stop and wait can only send one packet at a time. Go back n sends n packets and waits for acknowledgement. SR, the sender can transmit up to n packets, but instead of retransmitting the full window, they can choose to only retransmit the corrupted or lost packets. Based on efficiency. Stop and wait, it is least efficient as it can only send one packet at a time. Go back n is a much better algorithm, however, can become inefficient as if a packet is corrupted, the sender would have to transmit the complete window of packets all over again. In case of SR, which is found to be the most efficient, it can only retransmit the lost packets or the corrupted packets. Moving on, we have client-server UDP communication. The process and the codes will be explained hereafter. Now we have Cisco Packet Tracer. The activity included adding an additional PC and enabling communication with all the other 4 PCs. This is the client-side code. First of all, I've imported the socket library. I have declared 3 variables. First is server name, which stores the address, the server port, and the message, which is hello, which I'm trying to send to the server. Now, first of all, I've created a client socket using the socket library, and the arguments that I've given is to use IPv4 and UDP for communication. Now on line 8, I send a message. I first of all encode the message and then send it to the server by giving in the arguments to the send to function as the server name and server port. After that, I receive any of the response that I get from the server and store the server's reply and the server's address. I also decode the message that the server sends me and print it on line 10. After this, I ask the user to enter his or her name, and after that I send that name as well to the server in the same way as I did on line 8. After this, I record once again the server's reply and the server's address, and I again decode and print the server's message. After this, I close the client socket. This is the server-side code. I first declared 2 variables, which is server address and server port. I've also imported the socket library, using which I have created a server socket by passing in the arguments to use IPv4 and UDP for communication. I've binded the server socket to the address and the server port. First of all, I print that the server is listening, which acts as a diagnosis for this program. After that, the server constantly listens to any of the clients which are trying to initiate communication in the while loop. If any of the requests are received from any of the clients, the message and the client address is recorded. The message string is created by decoding the message received from the client. If the message is hello, which the client that I have programmed is sending, the server socket sends back to the client address a query which says hello, what's your name? After this, if any other message is received from the client, the dot split is used to split all the string message into different words, and the -1, the square bracket, is used to extract the last part of the string and store it in the variable name. After this, the welcome message string is created using the variable name, and the server socket sends this, encodes this, and then sends it back to the client. After this, the received name as well as the client's address is printed on the screen. Now I will show you a little working of this code. Thank you. For this activity in Cisco Packet Tracer, we were to add an additional PC. I've connected another switch to the router, and through that switch I've connected the 5th PC. In order to do this, first of all, I had to change the router's configurations in order to handle one more gigabit Ethernet connection. The IP address for it has been set in the router as 192.168.2.1 with a subnet mask of 255.255.255.0. After this, I changed PC5 settings to change the IP address to 192.168.2.4 and with subnet mask 255.255.255.0 as per in the given question. Now these are the results of the ping commands I've sent to the 5th PC from all the other 4 PCs. Routing protocols. The collection of established guidelines used by routers to communicate between sources and destinations is known as routing protocol. They merely update the routing table that has the information rather than moving it from the source to destination. Interautonomous system routing. Inter-AS routing is the protocol that uses the routing algorithm to move data across and within AS. It is sophisticated and dependent. The AS and the AS with which the contact is taking place should both have internet connectivity. Some popular examples of this are Baud Gateway Protocol and ISIS. After this, we have intra-AS routing, which only functions within the AS when using the inter-domain routing protocol compared to inter-domain routing or inter-AS routing. Intra-AS routing is less complicated and interdependent. Intra-AS routing requires knowledge of with just those components that are located within the AS, since it only communicates with other AS members. Some of the popular examples are OSPF and RIP. Now let's look at some of the routing protocols one by one. Open Shortest Path First, or OSPF. It uses the shortest path first algorithm or Dijkstra's algorithm and is an interior gateway protocol. In an OSPF network, each router or computer in a given area keeps an identical link state database that details the area's topology. Each router or system uses the SPF method to create a shortest path spanning tree with itself as the root employing the link state data. Some of the limitations of this protocol are load balancing, which is inefficient, scaling of OSPF problematic as it maintains multiple copies of routing data, monitoring of algorithm status is not possible. Some of the disadvantages are it does not scale effectively when additional routers are added to the routing domain, since more routers result in larger and more frequent topology changes as well as longer calculation times for end-to-end routes. It requires extra CPU processing power to run the SPF algorithm. RAM requirements are more as OSPF stores adjacency topology. It is more complex to set up, especially when AS is separated into areas. It is difficult to troubleshoot. Let's look at some of the advantages of this protocol. It is widely used for large heterogeneous networks. It supports both IPv4 and IPv6. No threshold on hop count. Loop-free topology due to the use of SPF algorithm. To reduce OSPF routing traffic and the size of each area's link state database, one can divide an AS into areas. Next up, we have Routing Information Protocol, or RIP. It is a dynamic routing protocol which employs hops. It might assign them a greater cost, as if they included additional hops in the path. Let's look at some of the limitations of this protocol. Network traffic is more as updates in RIP occur at frequent intervals. RIP only updates neighboring routes. This may result in non-neighboring routers not being updated as the information is not accessible. Threshold of hop counts is 15. This may result in unreachable routers which are remotely situated in a network. Some of the disadvantages of RIP are as follows. It's not always loop-free. Supporting just equal cost load balancing, it is inefficient and requires a lot of bandwidth. It also has significant advantages such as practical configuration, promoting load balance, supports almost all routers, easy to understand, generally loop-free. Next up, we have BGP, which is Border Gateway Protocol. It is an inter-AS routing protocol as compared to all the previous two routing protocols we studied. It supports next hop paradigm, which dictates that a packet of data goes to the next most optimal destination. Before selecting the best alternative for the next stop of data, BGP is able to scan all the choices. Some of the limitations are BGP routing tables may expand significantly and become challenging to manage as the size of the internet and the number of linked networks increase. Many attacks against BGP can cause traffic to be completely interrupted or redirected in the wrong direction. Configuring and managing BGP takes a high level of technical knowledge. Some of the disadvantages are as follows. There is no digital identifier built into BGP, which inherently makes it unsafe for network communication if no third-party safety protocol is used. Advertising by an AS might result in repeated advertising or loop. It is not considered as a stable RP. It does have the ability to detect packet loss and saturated transit services. Some of the advantages are as follows. BGP conserves network bandwidth. It supports classless inter-domain routing for IP address allocation. It supports third-party security tools and protocols. BGP allows authentication and also sends information regarding whether the router is reachable or not, which increases the network's overall efficiency. I'm analyzing DHCP on my local machine itself. In order to do so, I first open the terminal and ran these three commands given. After this, before that, I had already started the DHCP packet capture in Wireshark. And in order to filter DHCP, I just wrote the tag in the search bar above. And after that, if we look at the second DHCP discover, and after that, all the requests that I've sent, I've analyzed that, and the results with my IP address, transaction ID, hardware type, hardware length, and all, as well as my MAC address, is also visible in the DHCP packet. Thank you. ARP. The Address Resolution Protocol was created at a period when network security was still in its early stages. As a result, the protocol has no built-in security and is in clear text. It doesn't check ARP packets for validity and even accepts ARP responses when no ARP requests have ever been made. This has made ARP extremely vulnerable to attacks. Let's look at some of them in brief. ARP spoofing/poisoning. Here is the scenario. The MAC address of the attacker is linked to the IP address of a machine already present on the LAN by a hacker using fake ARP messages. A hacker modifies the company's ARP table such that it contains fabricated MAC mappings following a successful ARP spoofing. When a hacker's MAC is connected to the LAN, all communication intended for the infected LAN will go to the attacker instead. Next up, we have ARP flooding. In this attack, the attacker bombards the victim device with many ARP messages, overloading its ARP cache and leading it to discard reliable mappings. After this, we have ARP cache poisoning. The target device receives a huge number of bogus ARP packets from the attackers, flooding its ARP cache with erroneous MAC IP address mappings. After this, we have MAC spoofing. In order to intercept and alter network communication, the attacker modifies a device's MAC address to match another one on the network. And this is the end of the presentation. Thank you very much.